Let us begin our discussion of protein structure determination methods with a quick review of the representations that we will see frequently of biological molecules. Basically, we got space filling, we got surfaces, and we got cartoons. All of them simplify in one way or the other the information that can be very overwhelming. But let's just begin with van der Waals shells. These are spherical representations of each atom that correspond roughly to the van der Waals radii of each atom. This is also referred to frequently as CPK representations, which of course stands for Corey, Pauling, and Kultung, the trio that pioneered their utilization. And the color code is fairly standard, at least for the oxygen and nitrogens. We color them red and blue respectively. Carbon frequently changes, but often will be represented as gray. And you can see that the color coding alone does simplify how we would interpret this molecule as opposed to simple spheres, spherical of all uniform color. We wouldn't be able to see, for example, this, I'm guessing this is a glutamine, for example. But still, highly complicated. Another really useful way of representing a protein is in this solvent accessible surface area. This way of drawing proteins was pioneered in the early 70s. And in this case, I've drawn that surface as partially transparent. Let's skip over that for the moment, but just notice that the way this structure is defined is as by rolling in in silico or in your mind a H2O molecule that's represented as a 1.5 angstrom radius sphere or diameter sphere. We roll that over the surface of the molecule and we see that a water molecule, if we can consider ourselves to be a water molecule, doesn't see these perfect spheres, right? There's plenty of crevices and indentations that the water molecule cannot penetrate, and so we get a much smoother representation in this way. Under this surface, I've drawn a ribbon diagram, and here it is again without the surface. So this is a great simplification that allows us to visualize rapidly what both the secondary structural content of the protein is, as well as what the global fold of the molecule is. And we've talked about this before as a backbone trajectory. Peptide, alpha carbon, peptide, that the trajectory overall that those atoms take through the backbone is how we decide to draw the direction of this chain. So those are our standard representations. All of them have their advantages and disadvantages. And frequently, although I haven't drawn it here, the solvent accessible surface is also color coded according to electrostatic potential. So again, as with this representation, you get a sense of where the charge on the molecule might be. What do these things really represent? Well, in the end, we'd like them to represent atomic coordinates, and frequently those coordinates will be based on electron density, where the electrons are in the atom. This is an image of electron density. This is a benzene ring with a couple of chlorine atoms attached, and you see that the chlorine is of course much more dense than the carbon atoms, but we see that it's very simple to understand how then we would begin making our simple representation of these, which is just drawing lines. Of course, bonds are not lines, right? Bonds represent the sharing of electrons, but we can see that really the electrons are centered around their individual atoms, even in the case of a molecule such as this. Okay, but where we go is something that's complicated and maybe difficult to interpret to something that's easy to understand, which is just these balls and sticks that we tend to draw. The question that we're going to be addressing in the next couple of lectures, however, is how do we estimate this electron density? And we'll see. Hopefully we'll give you a basic sense of how we do that. We've seen this slide before. I'll just remind you why we care about molecular structure. Of course, what we want to do is assign a function or a malfunction to some structural component of a protein. Here's a ribbon diagram of an oncoprotein called RAS, and we see that in asterisks here are regions, amino acids that we frequently see mutated in different kinds of tumors. And we can easily see that since this is where the ligand binds to this is a GTP binding protein in proximity to those mutation sites, that's the basis of the disease. So without going into detail again about the activity of RAS, suffice it to say that we care about understanding and assigning electron density in proteins because that helps us understand the function and malfunction of proteins. But let's back out again to discuss electromagnetic radiation. This is a picture that you've seen frequently. This is the spectrum of electromagnetic radiation going from very short wavelength radiation, gamma rays and X-rays, very high energy radiation, to very long wavelength radiation, all the way out here to radio wavelength radiation. Lower energy, longer wavelength. And then, of course, we're familiar with this region, the visible region, with ultraviolet on the high energy end and infrared on the low energy end, flanking the visible spectrum. Okay, what about biological molecules? So I've labeled these different frequencies with the different methods that we use that electromagnetic radiation in as we interrogate the structure of biological molecules. So it's useful to note that X-rays have a wavelength that's on the order of the diameter of atoms or the length of carbon-carbon bonds. We're going to find that to be very useful in X-ray crystallography, for example. We use visible and wavelengths nearby the visible for looking at fluorescence of, for example, aromatic side chains. As well as the absorbance of side chains and peptide bonds. Peptide bonds also have a visible or ultraviolet absorbance. And then the other technique that we're going to discuss for determining biomolecular structure is nuclear magnetic resonance spectroscopy, and it just so happens that the resonant frequencies of these nuclei, protons, carbon, and nitrogen isotopes, are in the radio frequency range. So we can ring those atoms, if you want to think of them as little bells, we can ring them by hitting them with radio frequency radiation. So all of these various frequencies of radiation are responded to by different components of the protein. A quick interlude with how we image things. This is just a cute way to show you newborn pictures of my son. This is an old picture now. But we say that a lens has a focal length f and presents at the other side a focused image at an inverted image at the 2f focal plane. So there's the focal plane and there's the 2f focal plane. The details of this we're not going to go into, but let us say that an important concept is that there's a limit of resolution using this kind of lens system. It's called the Abbe limit, and it's about 1/2 of the wavelength of the radiation that's being used. That's very important because that says that we can't use visible radiation to image anything that's lower than some minimum threshold size, 250 nanometers or so. Below that, we can't use visible radiation. What does that mean? It means we can't see it, right? We can't image it with our eyes, which respond primarily in the visible range. So what do we do beyond this Abbe limit, where proteins, by the way, happen to reside? Well, yeah, so how do we image biological molecules? So let's think again about molecular scales and where those scales reside with respect to electromagnetic radiation. Shortest visible wavelength is about 400 nanometers, 450 nanometers. Beyond that, we're into the ultraviolet. Remember that 280 nanometers is the absorbance of tyrosine and tryptophan. Our average protein, let's use myoglobin since we've been using myoglobin as an example for other things so far, is about a nanometer in diameter, or 10 angstroms in diameter. So if we compare that, we see that there's the wavelength of some blue light relative to the diameter of the protein, and we see that the diameter of the protein is way smaller than the Abbe limit, so we can't use visible radiation to interrogate proteins. Now, let's hasten to add, however, that we can use visible radiation to detect proteins if those proteins happen to have a chromophore, as myoglobin does, right? Remember the heme that absorbs visible radiation. Still, saying that there's heme present in myoglobin is a far cry from assigning three-dimensional coordinates to every atom in myoglobin. So to see how we move beyond this limitation of visible radiation, we'll come to the next video, 3.2, in which we discuss X-ray crystallography. See you there.